Welcome to EE 544 on Tuesday, February 4th, 2014.
Thank you very much. Good morning. Good morning. Good afternoon, everybody. Let's wrap up the material on the architecture. We need to get into the modeling. By the way, I posted a couple of charts on the modeling, the nonlinearities and the noise, which will start after we go this way here quickly. Okay, so let's continue our discussion on the architectures of our receiver. We saw that the first one is called super heterodyne. In a super heterodyne, you are going to go through what? RF and then what? IF and then what? Baseband. Notice, by the way, the IF might be what? Multiple stages. You follow me or not? In other words, you could go what? IF1, IF2, and so on and so on to the baseband. In the direct convergence, sometimes they call it what? Zero IF, or they call it what? A homodyne receiver. A homodyne receiver, you are going to what? You are going, let's see it from here so that you can see it. This is a block diagram, simple block diagram. What do you see? This is the received carrier. Yes? What is this one for? This is for the band selection. You are going to select the band. Clear? You are going to what? Amplify the signal. Clear? Amplification of the signal, the low noise amplifier. What do you see right away? You see the what? The IQ mixer. Are you following me? The IQ mixer. And you are what? You are down converting the spectrum from around what? From RF directly to what? To the baseband. Directly to the baseband. Clear? Okay. And what are you going to do in the baseband? Once you, notice by the way, did you down convert the entire band? You converted the entire band from RF to the what? To the baseband. What is this doing? What do we call it? What is this one called? That's the channel selection, which means what? The channel selection filter, which means the channel selection is done in what? In baseband. Yes? Easier to design a low pass filter than a band pass filter. And that's much easier to do. So you are going to select in the baseband, you are going to select only the desired channel. Clear? Answer me the following question. By the way, afterwards you are going to what? You are going to convert it into analog to digital conversion. Answer me first of all the questions about the A to D. Will this one be a little bit easier to do? The A to D. Why? Because you are what? You are going to what? You are going to deal with what? With baseband signal, which means what? You don't need that high sampling rate. Clear? You don't need that high sampling rate. Now, explain this one to me right now. This is the what? This is this oscillator. This oscillator. Why is it variable? Is this a synthesizer? That's a synthesizer, which means what? We need an RF synthesizer. It's still variable. Why? Can you tell me why? To select different what? To try to get different what? Different channels. Every time the desired, when you set this one up, the desired channel will be centered around what? Around the origin. Did you get this or not? Okay. This is a complete, we'll get to the problems in just a second. But did you understand the idea? Now, we don't need what? We don't need filtering in the what? IF. We don't need, do we need the image rejection? We don't need image rejection. We don't have an image. So all of these, the filters that we saw that requires what? High Q, which means what? Higher order filter are what? Eliminated. But the problems that this one associates with, the new problems that were not available in the what? Heterodyne. We need to understand that. But just to make sure that you get the diagram correctly, tell me, what is this? This is the antenna. That's the diplexer to separate the transmitter and the receiver. This is the what? The low noise amplifier. This one, by the way, is the channel select. Yes? The low noise amplifier. Yes? This filter is to what? To remove any nonlinearity components that results from what? From the amplification. Yes? This is to adjust the what? The proper gain. We call it the what? The RF VGA. What is RF VGA? RF, voltage, gain, variable, I said voltage, variable gain amplifier. Clear? Why do I say RF? I say RF because it's operating in what? In the RF. Yes? Then I go right away to the what? To the demodulation. This is the demodulation. How many mixers do we have? How many down converter we have? We have only one. We do it in one stage. Yes? This is what? This is the local oscillator. A question. Is this a synthesizer or is it an oscillator? It's written LO, but in reality, is it a synthesizer or is it a local oscillator? This is a synthesizer, just like I showed you a moment ago. Where is it? I have no idea where it is. Here. This is a synthesizer. Clear? This is the IQ. Yes, this is the 90-degree phase shift. Yes or no? To generate the cosine and the sine. Tell me what is this one is doing. That's the channel select. The low pass filter is the what? Is the channel select. Yes or no? And then what? This is an amplifier, an audio amplifier, baseband amplifier to the what? To the AD, ADC, or DAC. Clear? Okay, now, what is the problem? Let's see if you can help me with, I will get back to this in just a second, but let's understand what is the problem associated with 0IF. The first one, it's called what? Local oscillator leakage. What does that mean? That's the local oscillator. Yes? If there is no proper isolation between the ports, there will be what? Leakage. Leakage from where to where? Listen to me. By the way, how many ports does it have? It has 3 ports. What are they? The RF port, the local oscillator port, and the what? IF port. Is it possible that I get a leakage from the local oscillator port to the RF port? And then what will happen? It will mix with itself. What do you get by mixing a cosine with yourself? You get a DC component. And that, we did not worry about it in what? In the super heterodyne. Because in the super heterodyne, we went through what? IF and then what? Baseband. Did you get my point or not? In here, where is the DC component? Can you show me? What is this, first of all? What is this? That's a low pass filter. That's the channel select. Clear? By the way, you might say, Professor, how come you are only showing one mixer? Where are the IQ? I'm only showing you what? One of the channels. Did you get my point or not? One of the channels. Okay, this is the channel select. Where is the channel select? It's this one. Yes? Did it have a DC? No. Did the channel, the desired channel, originally, did it have a DC component? If it had a DC component, then in the spectrum, I will see a what? I will see an impulse at what? At f equal to 0. If it has a DC component, discrete DC component. Yes? But it does not have a DC component. So where did this come from? Where did this impulse came from? This impulse came from what? From the self-mixing of what? Self-mixing because of what? Because of the LO leakage. Yes? Even worse is the following. Look at the worst thing here. You are going to what? You are going to leak to the input of what? To the input of the LNA and then what? Back. Which means what? You are also going to get what? The gain of the what? The low noise amplifier into the picture as well. Yes? Will the DC be higher or lower? What do I say? I say the offset, the DC offset is what? Time variant. Time variant means what? It's going to change. As sometimes its value is this. See, if the value is fixed, is it easier to remove it? But if the value is changing, you need to keep track of that changes. Did you get this or not? No response. Okay. Can you explain to me? Did you understand the DC offset? Okay. Can you explain to me the spurious emission? What spurious emission? Spurious emission is that the local oscillator will leak all the way to the what? To the antenna and radiate that signal. Are you following or not? To other channels, this will be a what? An unwanted channel. That's a spurious emission. Clear? No response. Clear? Tell me what is the problem with this one. What is the problem with this one? What happened? I have a what? This is the desired channel. Yes? And I have a strong interferer. Why is it a strong? Why is it a strong interferer? Because the transmitting transmitter, that interferer, the transmitter happens to be what? Close to the receiver. By the way, it is within the what? Within the desired band, which means what? This filter was not able to what? Remove it away because it's within the desired band. Clear? Okay. What does it do? It goes through the LNA and the what? The leakage is now from where to where? RF to what? LO. Did you, rather than from what? The LO to what? RF. Right now it's from RF to what? LO. Let me ask a question. If this one leaks to the output, is there a harm done? Did you answer my question? No? You didn't understand my question. Listen to the question. If this interferer leak to this port rather than to this port, is there a problem? No problem. Why? Because this filter is a what? It's a low-pass filter, so it will get rid of that leakage. Did you get my point or not? Yes or no? Okay, good. Now, it will what? It will mix with itself. Yes, it will mix with itself. Now, you might say so, but remember, this is a strong interferer that also went through what? An amplifier. It's a low-noise amplifier, which means what? The DC component will become even what? Will become even higher. Did you get my point or not? Yes or no? Okay, good. Now, could it also mix with what? With the RF. Could it also mix this one? Could it mix with the RF? It could mix with the RF, generating what? Generating might be these components. Are you following that? But I don't worry about them. Why? Because I'm going to use what? A low-pass filter in here. Clear? How about this situation? How about this situation? I have a what? I have a nonlinearity in our what? Low-noise amplifier. Yes? That nonlinearity happens to be what? Even order. What does even order mean? I will show you that in just a second when we get to the nonlinearity. Even order means what? Means this one is raised to the what? Raised to the power 2 or raised to the power 4 or 6 or whatever. Even order. Yes? Look at this situation. I have two strong interferers. Yes? Let's call them what? F1 and F2. That happens to be what? Close to each other and within the what? Within the desired band, which means what? Both of them will go through the what? The band select filter. Yes? They get what? There is a what? A nonlinearity here of even order. Will this one generate intermodulation component of the second order? Yes or no? Which is what? What is the second intermodulation component? If I have, remember by the way, by the way, do I worry about harmonics? I don't worry about harmonics. Why? Harmonics is not going to go through a what? The low pass filter. Yes? But do I worry about the intermodulation components? What is it? For the second order, it's what? F1 minus F2, F1 plus F2. Yes? F1 plus F2, I don't worry about it. Why? It's not going to go through this filter. Clear? But F1 minus F2, if these two interferers happens to be what? Close to each other, the difference will be around what? Around the origin. In other words, very close to what? To the origin. Yes? Will it be within the desired band? It will be within the desired band. Are you following me or not? And remember, once it gets within the desired band, there is no way of what? Removing this. There is no way of removing this. Clear? Why? Because if you attempt to remove this, you are what? You are cutting part of what? The desired band as well. Clear? All of these problems, let me make one comment here. All of these problems, were they available in the super heterodyne? They were not available in the super heterodyne. By the way, in the super heterodyne, which type of intermodulation components do I need to worry about? I need to worry about odd order intermodulation components, which is what? 2F2 minus what? F1. Or 2F1 minus what? F2. In here is the second order. Clear? Clear? I want you to see this. I will get to your question in a minute. I want you to see this. Did this second order, did it get mixed? You lost me here. Concentrate. Concentrate. Where is the second order intermodulation? Where did it appear? It appeared in here. Yes or no? Okay. If this one get mixed with this one, not leaked, get mixed, do we have a problem? Why? Why I don't have a problem? Because this one is what RF. So when you mix this one with this one, it will become what? It will become centered around RF. Yes? What am I saying here? I'm saying that there was a leakage from the RF to the baseband. Yes? Which means what? It did not get what? Mixed. It just passed through the what? Passed through the mixer to the what? To the outgo. And this is this one. Clear? You see this? This means what? Leaked without getting what? Mixed. If it get mixed, one more time, if it get mixed, do I worry about it? I don't worry about it. Are you following or not? Because when you mix it, it's going to be what? Around RF. Clear? And this filter will get rid of it. Clear?
Okay, for the next comment, even if it's leaked, it will be centered around the RF, not in the basement.
Which one? Which one? If it is leaked, tell me which one are you talking about? This one?
Yeah.
If this one leaked to this?
Yeah, it's okay, the RF, isn't it?
Why? This one is the second intermodulation already appeared in here, which is the output of the amplifier. The intermodulation is not going to appear here. It's going to appear here. All the non-linearities. Let me jump a little bit. Jump a little bit. This is one that we'll discuss next. Do you see this one? This is the non-linearity I was telling you about. Where is this V naught? This V naught is the output of the amplifier at this point. Clear? Okay, I'll get to this in a minute. Can you give me a minute? I will show it to you. Yes.
For the system receiver, in the last mixing stage, are we going to suffer from the LO leakage?
A little bit. A little bit. But that is what? That is, by the way, you always suffer from what? The leakage. Are you following? In the superhydrodyne. But not at the first stages, at the low. Which means what? It means that throughout, by the way, which one has more filters along the chain? The superhydrodyne. The more filters you go, it means what? You are getting rid of many what? Interferers along the way. Did you get this or not? Whereas in here, it's just that filter and the what? In the basement. Clear? Clear? I cannot hear you, my dear. One more time. If the LNA has a what? It has a what? Third order distortion. Third order nonlinearity. If it mixed with, by the way, this one, it will be what? 2F2 minus what? F1. Yes? 2F2 minus F1 is very close to what? Let's assume they are very close to each other. Yes? So 2F2 minus F1 will be very close to the desired one. And when it mixes with this one, you might have a problem because it will be very close to the DC. Yes or no? A lot of, see, the thing is that I don't want you to think about an architecture as always it is what? All advantages and no what? Disadvantage. Every architecture has some advantage and some what? Disadvantage. Did you understand what I just said? The other one, which I did not mention it, let me mention it right now, is the, what is known as the what? As the, let me see, as the flicker noise. Are you following me or not? The flicker noise. The flicker noise is not the same as what? Thermal noise. The flicker noise has a power spectral density which is proportional to what? 1 over what? F. If it is 1 over F means what? Most of the power. Remember, power spectral density is what units? Watts per what? Hertz. If you take the area under the power spectral density, you are calculating the noise power. Yes or no? Most of the noise power will be concentrated at low frequency components because the spectral density is proportional to what? 1 over F. So when F is small, this one is high. Clear? We did not have a problem with this in the case of the superheterodyne because we were dealing with what? We were dealing with RF, IF, and so on. So, clear? Clear? Another problem. Let's see if you can tell me. Are you following me so far or not? Tell me if you see another problem in here. Which is the following? I will tell you what are possible solutions in just a second. Where is the chart? Huh? Here. Where is the IQ is done? Is it done in RF? The IQ, is it done at RF? It is done at RF. When you do with IQ at very high frequency, by the way, what are we talking about? What frequencies? For example, if you are using an 802.11, we are talking about frequencies in the range of what? 2.4 gigahertz or what? 5 gigahertz and so on and so forth. Clear? These are not low frequency components. Designing the IQ, you need to be very precise in terms of what? Making sure that the I channel and the Q channel are what? Balanced. Are you following me or not? Because any amplitude variation or phase variation, let me show you this so that you can understand what. Any gain mismatch, epsilon, or what? Phase mismatch results in what? Result in some of the what? I channel getting into what? Q channel, and the Q channel getting into what? I channel. Now you might say, so what is the big deal? The big deal is that most of the time the information modulated on the I channel and the information modulated on the Q channel are coming from different what? From different sources. Are you following me or not? From different information sources. The beauty of the I and the Q is that using, do you understand, first of all, what is the beauty of the IQ? We'll talk about it in detail when we get to the modulation. Are we using the same carrier? Which means what? We are not using two carrier frequencies. We are using what? One carrier frequency that supports what? Double the rate. Which means that you are improving the bandwidth efficiency. What is bandwidth efficiency? Units, bits per second per hertz. Yes? Why can we afford that? We can afford that because we are banking on what fact? The fact that the sine and the cosine are what? Orthogonal. So when the sum, which is what? Sine plus cosine, when the sine get multiplied with a cosine, you will get what? 0. You will get just the sine. Yes? And the other branch, you will get what? Cosine. Yes or no? But if it was not balanced properly, you are going to get what? Part of the I channel will be what? It will be cross-talked into what? Into the Q channel and vice versa. Clear? Resulting in what? Resulting in increase of what? BER. BER stands for what? Bit error rate. Clear? By the way, if you look, we'll talk about this later. Are you familiar with the I diagram? I? No? No? No, you are not familiar. I will show it to you when we get to the modulation. The I diagram is a procedure where you can see what, whether the situation, bit error rate and stuff is what is really bad. If the I is closed, what does it mean? You are going to get too many what? Too many problems. Clear? Clear? If the I is wide open, it means what? It means the effect of noise and band limitation is what? Is limited. The intersymbol interference is limited and so on. So clear? But I will show it to you in detail, the I diagram. You need to understand the I diagram. Clear? Clear so far or not? Okay, good. Now, so keep that in mind. Even distortion, I already explained it to you. Yes? Now, let me ask you a question here. Can we get out of the DC offset? Can we get rid of this guy, this DC offset? Now, if I use AC coupling, what does AC coupling mean? I put a capacitor in what? In series. You know that the DC does not go through what? Through the capacitor. But the problem is that once you put the capacitor in series, you have created a what? A high-pass filter. And if you created a high-pass filter, what does it mean? It means the low-frequency component will not go through. But the whole thing is what? The whole thing is what? Low-frequency components, because this is direct conversion. So you are not only what? You are not only blocking the DC, but you are also blocking the what? The desired channel. Yes? One possibility to overcome this is to use signaling scheme that is what? Not centered around the what? Origin. It is centered a little bit what? Away from the origin. Are you following on that? So that you can design the blocking filter, which is what? The series capacitor, to remove only the what? The DC. Yes or no? In doing so, let's see some numbers so that you can get the idea. Listen to me. The rule of thumb. The cutoff frequency. Can you show me where is the cutoff frequency of a high-pass filter? A high-pass filter. What does it look like? Yes? Where is the high cutoff frequency? Is this. The rule of thumb is what? Is that the cutoff frequency of the high-pass filter should be less than 0.1% of the what? The data rate. What does that mean? Can you tell me why am I comparing it with the data rate? You lost me here. You lost me. 1 second. Let's see if you still remember. I doubt it, but let's see if you still remember. This is the what? This is the pulse. Just a single pulse. Yes? From here to here. This is what? TB over 2 minus TB over 2. Yes or no? What is TB? TB is the pulse duration. Yes or no? And what is 1 over TB? 1 over TB is the bit rate. T sub P is the bit rate. Yes? What is the frequency response? What is the Fourier transform of this guy? The Fourier transform of this guy is what? Sinc function. What is this point? This is F now. What is this point? 1 over what? TB, which is equal to what? RB. So what do I say? I say the bandwidth is almost equal to what? To the bit rate. Do you understand that or not? If you neglect all of these side lobes fluctuations. Clear? What does this one tell you? It tells you 0.1% of what? The data rate. Which means what? 0.1% of this value. Did you get this or not? Okay, which means what? Listen to me. For example, if we take 2G TDMA, 2G TDMA, this is the US system, not GSM. Are you following me or not? GSM has a higher rate. 2G TDMA system. Anybody knows what we call this? Anybody? IS? Anybody? 535. Is he talking about standards or not yet? Not yet? Anyway, it's called IS. Don't worry about this. Don't worry about this. This is too much detail. It's called IS54. Clear? Clear? Don't worry about it. IS is the interim standard. Don't worry about it. I just want you to understand. By the way, this is the AT&T solution for second generation, not third generation. Clear? The UCDMA, the data rate was what? 48 kilobits per second, which means what? It means from here to here is what? 48 kilobits per second. So if you take 0.1%, we are talking about what? 50 hertz. Do you understand that or not? Okay, which means what? It means that when you design your filter, this one here is going to be what? 50 hertz, which means what? The DC will not go through, yes, but anything between 0 and 50 will also what? Not go through, yes? But if you use signaling scheme that has a spectrum like this, then what? Then you afford what? You afford certain. Did you do the homework? Did you look at the solution to the first homework? How many of you looked at the solution? Did you see the rest? You did not even bother. The rest were watching Super Bowl. Yes? Okay. Anyway, if you see the what is known as what? The biphase. I gave you two signal schemes. One of them is called the NRZ. NRZ means what? Not return to zero. The other one is a biphase. Biphase, sometimes they call it a Manchester code. You saw that the what spectrum of the Manchester code is not centered around what? The origin. It's a little bit away from the origin. Clear? If you use that, then the effect of this DC component is what? Is negligible. Clear? Another way they do it is through the use of circuitry, other circuitry, which is called what? DC offset cancellation. What do they do? This is especially in time division multiple access. Let's see if you remember. In TDMA, the mobile, or the base for that matter, the TDMA, each mobile is going to be transmitting during a certain what? Time slot. Do you understand that or not? During other time slots, that does not belong to you, you are still, of course, generating traffic, but the traffic is going to be what? Buffered until your time slot comes, and then what? You burst. Yes or no? What you can do is what? Estimate how much is the DC offset during your what? During your time slot, yes? And try to what? Offset it. Offset it means what? Cancel it during the time slots that you are not what? You are not transmitting. You can do that on the side. Did you get my point or not? You can do that on the side. However, the problem with this is that interferers don't care about what? Time slots. Interferers can come at any time slot. Did you understand what I just said or not? Yes or no? So even though during the time you are trying to what? Offset the DC, there could be what? Interferers that change the what? Change the DC. Clear? Clear? Okay. But that is, by the way, a lot of circuits using cancellation techniques to get rid of what? To get rid of the DC, sometimes to get rid of the echo. They call it what? Echo cancellation, especially for application that requires what? That deals with audio processing, audio or voice. Are you following me or not? We have a professor in the department, has a company, but I cannot pronounce his name. It's very difficult. Professor Karikokos, or something, I mean, very hard name to pronounce. I cannot pronounce his name. I give up. You can tell that he's a Greek guy. He has a company, just a company, that he deals with what? Generating what? Generating circuits that deals with what? Echo cancellation, DC cancellation, and so on. So all of these things. Clear? Okay, good. Now, any question on this? Did I miss anything? Let me see if I missed anything. Okay, the IQ, again, as I told you, the balancing is what? This I will assign it for a homework. The homework for this weekend, this coming weekend, I will ask you what? Introduce a mismatch both in the amplitude and the what? Phase. And I want you to track the what? The I and the Q. Yes, you will see part of the Q will appear in where? In the I, and part of the I will appear in the what? In the Q. Clear? That's the opposite that we talked about. The measurement showed that if there is a 5-degree offset, it's a 5-degree offset will represent a what? 1 dB degradation. Are you following or not? 1 dB degradation. Clear? Which means what? When we get to the link budget shortly next week, the following week, not next week, following week. When we get to the link budget analysis, we see that we need to introduce in the link budget some degradation losses. 1 dB there, 2 dB there, based on what? Based on the hardware degradation. Are you following me or not? It's not only just what? Just environment or a propagation or something. Sometimes it's when in the implementation you are going to what? You are going to get some losses. Clear? Okay. This one here, we will talk about it especially in detail when we get in a minute on the nonlinearity, which is the even order distortion. Clear? Clear? The flicker noise I already talked about. The leakage. What is the LO leakage? We are not talking about the DC. We are talking about the spurious emission. The FCC requires impose an upper bound of what? Minus 50 to what? Minus 80 dBm. dBm is what? Watts. That's what the spurious. Are you following me? From what? From your local oscillator to the what? To the antenna. Clear? So you need to make sure that that we don't have that problem. Again, as I told you, it's less severe in the heterodyne receiver because the heterodyne does not use what? Does not use the local RF. Is not the same as what? It's not the same as the DC. Clear? Okay, this is a diagram just to show you some numbers. This is the desired channel. I want you to see the DC. The DC could be what? This one is what? 100 microvolt. This one is what? 10 millivolt. Do you see that the DC is much stronger than the actual? Are you following me or not? Why? Why is that? Because the DC could result from what? Strong interferers mixing with themselves, or a local oscillator mixing with what? With itself. We are not talking about weak signals. Clear? Clear? Okay, so keep that in mind. This is again the difference between what? Between between the super heterodyne receiver and the what? And the direct converger receiver. All of these are what are gone. It's much simpler in the design. Okay. One possibility, again, that is used in some wireless devices. Some possibility is to use what is known as what? Low IF. Low IF. What does that mean? You are not going to what? Go directly to what? To the DC, but you are going to down convert your RF signal way, way down, but to a point which is what? Not 0 IF, but a what? A low IF. That low IF is roughly, as I will show in just a second, let me show it to you so that you understand what I'm talking. The IF frequency is chosen to be roughly 1 to 2 times what? The channel bandwidth. What channel bandwidth? When I say channel bandwidth, what bandwidth? What channel? The desired channel. And the desired channel, if it is a narrowband channel, 1 to 2, it's still what? It's still a small. Did you understand what I just said or not? Why? Why you are not going all the way to DC? You are not going to go all the way to DC to prevent what? to get rid of the DC offset, all of these things that we just talked about. Clear? But if you go to the low IF, do you still have a problem? Do you still have a problem that an image could be created? The image could be created. We are getting back into the what? Into the the image. Clear? But what? The sampling will become a little bit what? Easier. Did you answer what sampling means? I'm talking about the ADC, because instead of what? Sampling at IF, you are sampling at what? Low IF. Yes or no? And low IF means what? Means the sampling rate is going to be a little bit what? A little bit lower. Clear? Clear? Okay. So the desired channel is offset from the DC. The signal is again, of course, passed through an A to D converter. Yes? Yes? No. And this is the receiver. Where did I show you the receiver? Here. This is the receiver. Okay, so this is the RF. I'm going to download it. This is the desired channel. Do you see this? Sorry, this is the low IF. Are you following me or not? This is now the low IF, where this one is centered around what? Around the base. Here is centered around what? Around some low IF. Clear? It's low IF. Yes?
Yeah, the filter there in the chain, is it a low-pass filter or a band-pass filter?
Which one?
The filter after the mixer. Is it going to be a low-pass filter?
I'm not getting it. You mean this one here? That is a low-pass filter. This is a low-pass. Why does it have to be a band-pass filter? It's a low-pass filter, but it is what? It is, this is the IQ. We are going to do the demodulation. Are you following me?
The frequency has to be after the low IF that I chose, isn't it?
Yeah, but the low IF is very close to the baseband. I just told you it's 1 to what? To 2 times the baseband. It's still very close. Are you following me on that? It's just away from what? It's just away from the origin. Clear?
But the DC will appear, isn't it?
The DC will appear, but you are not going to select the DC because the DC is not at IF. Are you following me on that? Okay, good. Now there is the problems, by the way, the problems with the low IF. Again, some method for what? The image rejection has to be performed. Are you following or not? You are still going to be able to what? Get the image because the desired carrier is converted down to IF. So image rejection needs to do that. And when you put, by the way, because you are doing the image rejection, where is the image now? Is it at the RF or the IF? The image is in the IF, which means what? At low frequencies. You agree? And if it is at low frequencies, you can design the image rejection on what? On board, rather than what? Off board. Are you following me or not? Cannot hear you. But on board, you are not going to get much what? Rejection. You are going to roughly get what? 40 dB. Why? Because you cannot afford to design a filter with higher order on what? On chip. You can do that off chip, but on chip you are not. So it's not going to be what? It's not going to be. It's not going to provide you with much rejection. And again, also the blockers, yes? Blockers means what? A strong interferer in the vicinity. They will get what? They will also get what? They will also get folded into the what? Into the IF, making it just like we saw in the case of the superheterodyne. Yeah? Okay, makes it even, makes it also harder than what? Harder than to remove the interference. Okay. Another type of receiver, by the way, in this class, I'm only going to hold you responsible for the superheterodyne and the what? The zero IF. All of these are just showing it to you. Are you following? I'm just showing it to you. Another one is a what? Is a wideband IF with double conversion receiver. Double conversion. So you can see that you do have what? You do have 2 local oscillators. Are you following? 2 IQs. Now, one of them is what? If you want to make them, one of them is fixed, and the other one is what? Is variable. This is where you are going to do what? The channel selection, and this is what? The first stage of the what? Of the down conversion. Clear? Clear? Okay. Now, again, there is no local oscillator present at the carrier frequency. Do you understand why? In other words, this one, if it leaks to here, there is no what? It's not at the same frequency. Did you get my point or not? Okay, good. Reinforce, again, by the way, reintroduce the image problems, again, every time. Utilizes IF channel select synthesizer. Where? Can you show me where is that? In the diagram. There's this one, not this one. Are you following me or not? Cannot hear you.
Yes.
Okay. This one, by the way, later on, how come nobody said, how come I have 4 circles? But I will show it to you when we get to the modulation. You are going to use 2 sets of what? two sets of IQs. Did you answer what I just said or not? Yes? Okay, but I will show it to you when we get to the modulation. Don't worry about it right now. Okay, now, again, the advantage of the wideband IF is what? Is that we don't have channel select at what? At RF. The channel select is at where? It's at the IF. Are you following me on that? So no RF channel select, the frequency synthesizer required. Which one is easier to design? A frequency synthesizer at IF or a frequency synthesizer at RF? At IF is much easier. Are you following me on that? Okay. Again, no local oscillator operating at same frequency. We already talked about this. Remove the need for high Q, discrete bandpass filter. When you say discrete bandpass filter, what does it mean? It's not integrated within the same chip. Achieve image rejection without a passive phase shift filter in the signal path. Yes, which means what? You could use which type of image rejection? The Weaver image. Remember the Weaver? We had two sets of this without putting 90 degree on the signal path. Clear? And again, the filtering is done in baseband. Disadvantage: additional mixers. You are going to use all of these mixers in addition to the what? To the original ones. Are you following on that? All of these required for the IR and so on and so forth. Hence, more power requirement, more noise, and so on and so forth. And again, it's limited by the what? The gain matching and the low oscillator deviation from the quadrature and so on. Another type of receiver is called what? Subsampling. What is this all about? What does the Nyquist tell us? Nyquist he told us is the following, is that you can recover a baseband signal, yes, if you sample it at a rate of what? Twice the highest frequency component being what? Sampled. If you look at the RF, if this is the RF, this is the RF channel, what is the highest frequency? The highest frequency is here. If you are going to sample it twice as this one, yes, twice as this one, you are going to end up with what? A very high sampling rate. Are you following me on that? Especially, again, as I told you, especially if you are operating in the gigahertz range. Yes? But Nyquist also showed us, this is what kind? Is it a baseband or is it a passband? This one. Is it a baseband signal or is it a passband signal? Passband signal. In a passband signal, you still can what? Sample and recover the original signal if you sample it at least a rate, which is what? Twice the bandwidth, rather than what? Twice the highest frequency component in the signal being sampled. Did you understand what I just said or not? The bandwidth is what? Relatively narrow if we are using what? Narrowband modulation techniques. Are you following me on that? The narrowband is relative. That's why we call it what? Narrowband modulation techniques. Clear? The narrowband is a little bit what? It's a little bit narrow. Clear? And this, again, as I told you, I would just show it to you, but I will assign it for homework. I want you to see that if you sample a passband signal, I want you to see the diagram so that you understand. This is the RF. Yes? This is the baseband. Oops. This is the band select filter. Yes? LNA. Image reject. The mixer. Yes? So, by the way, so far, listen to me. So far, is it the same as the super heterodyne? The same as the super heterodyne. This is the IF filter. Yes? Okay, which is what? Which is at a fixed IF frequency. What do you see then? What do you see is that you are going to sample it here. Are you following me or not? Rather than what? Sample it at what? At the baseband. You are bringing the sampler what? Closer to the what? To the antenna. Are you following me or not? Okay, and when you sample this one is a sampling at a rate of what? Twice the bandwidth. So for example, if you take an example, GSM operating at 1.8 gigahertz. This is the European, by the way. In the US, they operate at 1.9 gigahertz. GSM is what is referred to as what? The PCS. PCS stands for the Personal Communication Services Systems. Clear? Clear? Okay, third generation test. The IF carrier is how much? 246 megahertz. Yes? The bandwidth is how much? 200 kilohertz. When I'm subsampling, I'm what? I'm going to use a sampling of what? Twice 200, which is what? 400 kilohertz, as opposed to what? As opposed to using twice Very close to what? Twice times what? 246. Did you get this or not? Yes or no? Now, what I'm going to ask you in the homework, I will tell you what? Start with a what? With the passband. Is this a passband? Why? Because it is centered around what? Around the carrier, whatever it is. Yes? And I will tell you what? Sample it at a rate which is what? Twice. And you will see that you will be able to what? You will be able to recover the original signal from what? From the subsampling. Do you understand what you mean by subsampling? Subsampling means what? Don't take as many what? As many samples. Clear? Okay, this I will, that's why. But if it's greater than 2 times bandwidth, must be satisfied to avoid what? Destructive aliasing. Clear? Otherwise, there will be aliasing. Aliasing means what? Folding of the spectrum. Did I show you aliasing before? I didn't? Have you seen aliasing before? Do you know what it is? I know. Do you know how? No, what signals? Okay, aside. I will never be able to finish if I keep saying aside. Okay, let's see if you can help me here. This is a mixer. Sorry, this is a sampler. And let's assume this is the signal x of t with the following spectrum. This is the spectrum. This is f sub m minus f sub m. Yes? Yes? I'm going to sample it. This is the sampler. And let's assume, just for simplicity, that the sampler is an ideal sampler, which is what? N minus what? Ts. Well, this is what? Delta N equal to what? Negative infinity to infinity. And what is this? This looks like this. Are these impulses? And these are impulses. I cannot have them in the real world. Are you following me or not? This is just approximation. Clear? What am I getting? I'm getting xs of t, which is equal to what? X of t times xs of t is what? The sampled version. The sampled version. X of t, xs of t equal to what? X of t times what? Summation delta t minus nts. Yes? Is this a periodic signal, by the way? Okay. What is the Fourier transform of a periodic? First of all, can I take the Fourier series? Oops. Can I take the Fourier transform of both sides? Multiplication in the time domain corresponds to what in the frequency domain? So what do I have? Xs of f, which is what? The spectrum of the sampled signal. The spectrum of the sampled signal is what? Is x of f, which is the spectrum of the original, yes, of the baseband. What is this? Convolution. What is the Fourier transform of a periodic impulse? 301. 301. If I have a periodic impulse train, in the which domain? In the time domain. What is the Fourier transform of this? 301. 301. Nobody remembers the 301. I would assume you also take it in 475. Did you take 475? Did you discuss this or no? Did you take it in 448? Who took 448? Anybody? Did you discuss this? Okay. Okay, so bear with me. Bear with me. The Fourier transform of a what? Of a periodic signal, any periodic signal is a bunch of what? Impulses. Are you following me or not? If they happen to be what? Impulses in the time domain, what will it be in the frequency domain? Delta F minus what? N Fs. Where Fs equal to what? 1 over what? Ts. Yes or no? Okay, that's equal to. This is from Fourier transform. I will be posting tables for the Fourier transform tonight when I get home. Somebody remind me, please. What do you get by convolving a function with an impulse? What do you get when you convolve a function with an impulse? What do you get? 301. 301, help me. What do you get when you convolve a function with an impulse? You get what? The function shifted to where the impulse is what? Located. And you don't get the impulse anymore. Yes or no? Okay, so what do we get? Give it to me. Can I get this inside? Why? Because summation is with respect to what? With respect to n. So what do I get? Summation n equal to minus infinity to infinity x of what? F minus n f s. And there is no delta. There's no delta anymore. Are you following me or not? Can you sketch this for me? What is this? This is spectrum duplicated how many times? Infinite number of times, centered around what? F sub s, the sampling frequency, and it's what? Harmonics. So what do I get? I get what is this one? Which component is this? No. This component is when n is equal to what? 0. So you get the original spectrum. N is equal to 1, what do you get? N equal to 2, what do you get? This f sub s. N equal to 2? Yes or no? 2 f sub s. Okay, what is this value? F sub s minus what? F sub n. You agree? Now, in order to be, and the same thing here, in order to recover this, what do I need to make sure? I need to make sure that this point is to the right of what? This point. Yes or no? Which means what? F sub s minus F sub m has to be what? Which means what? F sub s has to be what? Agree? What if it's not? Can you tell me what the spectrum look like? If it is not, if not, this is what I have. Agree? Agree? That's the ALIZAHID. Did you get it or not? Yes or no? Okay. Now, listen to me. So when you sample a signal, at the beginning, you will see it like this. Anti-aliasing filter. And then what? The A to D, the sampling followed by what? The quantization followed by what? Encoding. See, the thing is that in here, what did I assume? I assumed the spectrum is band limited. Yes or no? If it is band limited, then this one is okay. You agree? But if this one was what? Band unlimited. Like what? Like the Fourier transform of a what? Of a square pulse, which is a sinc. In this case, no matter how large you take F sub s, there will always be what? Over aliasing. You agree with me or not? So you try to what? To get rid of as much as possible of what? Those side lobes from the sinc function before you do the what? Before you do the sampling. Clear? Clear? Cannot hear you. Let me ask you a question. True or false? Let me ask you a question. A signal can be time limited and band limited at the same time. Wrong. This is false. Are you following me or not? So if I want the bandwidth to be what? If I want the signal to have what? Band limited, that signal needs to be what? Time what? Unlimited. Are you following me or not? In reality, do I need a signal which is time unlimited? To see the signal, I have to wait till infinity. I don't have better things to do. Did you get my point or not? Cannot hear you. If the signal is time limited, then it is what? Band unlimited. Yes or no? Okay. Is it possible that the signal is time unlimited and band unlimited? Both of them are unlimited. Possible or not possible? You lost me here. Did you lose me? Did you lose me? Okay, your answer should be what? What do we care about this case? Do we care about this case? If the signal is time unlimited, the bandwidth is what? It is time unlimited and what? Band unlimited. Do we care about this case? But is this possible? It is possible. Just a quote. If I have x of t equal to what? E to the minus t, u of t. Is this band time unlimited? It goes from where to where? 0 all the way to what? Infinity. Yes? Do you remember what is x of f? 1 over 1 plus j 2 pi f. Yes or no? And what is the absolute value of x of f? 1 over 1 plus 4 pi square f square. Agree? How do I sketch this? Agree? Is it band unlimited? Band unlimited. Is it time unlimited? Yes. Are you following me or not? But I don't care about this signal. Am I using e to the minus t in the real world? Do you understand that or not? What in the real world, I would like the signals to be what? Time unlimited and band, I'm sorry, time limited and what? Band limited. Of course, I cannot do that. I cannot do that. I can only approximate. Clear? Okay, enough of this aside. Did you get it? Okay, what I want you now to see in the homework, I want you to see that if this signal is a passband signal, is this a passband or is it a baseband? Baseband. Why? Because its spectrum is around what? Around 0, a low frequency. But if this signal was a passband signal centered around, for example, IF, you will see that if you choose a sampling rate at least twice the bandwidth of the signal rather than the what? The height. By the way, in this case, the bandwidth and the highest frequency component are the same. Do you agree? Because you are measuring it from 0. Yes or no? What, by the way, what is the bandwidth of this? No. Oh, God, I have severe headache. The bandwidth is always measured for positive frequencies only. Are you following me or not? And what is the bandwidth of this guy? The bandwidth of this guy is from where to here. Did you get it or not? Yes or no? If you are dealing with passband signal, then the bandwidth is what? Is the highest minus the what? The lowest. Did you get it? Okay, so this is bandwidth. So in this case, is the bandwidth the same as f sub m? Yeah, so it's the same. But for a passband, is it the same? In other words, if I tell you this, what is the bandwidth? The bandwidth is this. Whereas what is the highest frequency? Highest frequency is this. Are you following me or not? Yes or no? Okay, good. Now, so I will do that, and you will see that as long as the sampling rate is at least twice the bandwidth of the passband signal, you will still be able to what? You will still be able to recover the passband signal. Clear? Okay, good. So, yes.
Yeah, in the subsampling application, what do we get of bringing the subsampling closer to the RF?
What do you get what?
What do we get of making the subsampling?
By the way, the idea of the software-defined radio is to what? Is to bring the sampler all the way to the what? To here, to the antenna, so that you what? You make your radio configurable via what? Via software rather than dealing with all of these hardware. Do you understand that or not? The problem, again, as I told you, I will show you that in just a second. The problem is that as you move this way, the carrier frequency will become what? Will become higher, which means what? The sampler needs to work what? Much faster. Are you following me or not? The resolution of the ADC requires what? Much higher. Clear? Okay, good. Now, so this I will assign it for homework. Let's look at just a general of this. This is the software-defined radio. When you hear the word software receiver, not defined, just software receiver, it means what? It means the sampler is all the way to the what? Antenna. That is called what? A software receiver, total software. Did you get this or not? When you hear the word software-defined radio or software-defined receiver, yes, the sampler is either on what? The sampler is what? Is at the output of what? Of the mixer, either in the RF or in the what? In the RF. But you still need a what? The front end of your receiver, the electronics, the front end of the electronics. And this is a diagram. You can see this diagram here. This is what? This is the duplexer here. This is the LNA. This is the image filter. So far, by the way, is it the same? Is it the same as the super heterodyne? It's the same. So this is what? The image reject filter. This is the mixer with a local oscillator. This is the IF. This is the what? The amplifier. And I'm going to what? I'm going to what? I'm going to sample it at what? At the IF. Are you following me or not? I'm going to sample it at the IF. I get what? I get a large number of what? Large number of samples. Yes? This one is the baseband, where you are going to do the what? The demodulation. Yes? You don't need that many samples. So in the FPGA, you see this FPGA? You are going to do what? Decimation. What does decimation mean? Decimation. Compression. You are going to what? You are going to get rid of what? Large number of samples, because this one is going to operate at what? At much less. You don't need that many samples. Did you get this or not? You don't need that many samples. On the other side, on the uplink, you are going to do what? Expansion. And by expansion means what? You are going to what? Interpolate those samples that what? That you disseminated, yes? You are going to interpolate it again. Did you get my point or not? Which means what? On the uplink, when you are sampling at what? At a lower rate, yes? Yes? You need to add what? You need to add more samples by interpolating between what? One sample and a what? Another sample to create a third sample in between. Clear? Clear? Okay, good. This is an example of a software-defined radio. And again, the advantages of it is that you can do what? Multi-mode operations. You can configure your machines with your receiver with a what? With the software. Are you following that? You are going to reduce the amount of hardware that you are using and so on and so forth. Fewer discrete one more time. Whenever you hear the word discrete components, what does it mean? Those components that are not integrated. Clear are the L's, C's, and so on and so forth. Vectors. Probability, flexibility to incorporate what? Additional functionality. It's much easier to what? Easier to add functionality via what? Via software. Did you get this or not? Clear? Okay. Several advantages. The other step, I showed you that maybe before, the other step of the software-defined radio is what is known as what? The cognitive radio. In a cognitive radio, remember I told you last time? Let's see. I don't know whether it's last time or not. This is what? This is the spectrum allocated to primary users. What does primary users mean? Those users that are paying what? Big money for the license. Yes or no? Remember what I told you before. There are some bands which are assigned to specific what? To specific servers. To specific service provider. Are you following me or not? For a cellular service provider, for example, Verizon. Yes? And there are other bands which are what? Which are offered based on what? The application. Did you get my point or not? Yes? Primary users are the ones that pay what? Large sum of money. Let's assume this is the spectrum that was allocated to them. And we notice, by the way, most of the time the spectrum is not what? Used. In cognitive radios will be able, those radios that are what? Equipped with this type of software will be able to what? Sense the spectrum, and if they see what? Idle things, they can use it, yes? But as soon as they what? As soon as they sense that there is a what? A primary users, they either jump. Look at this. They were operating in here because the channel was what? Idle. Somehow it came, this one came. What did they do? Poof, they jumped to another one. Are you following me or not? Poof, they come to another one. Yes or no? In order to do that, what do they need to be? They need to be very agile. The frequencies needs to be what? Very agile. And they need to be able to operate at what? Multiple bands. Yes or no? Cannot hear you. So you go through all of these things. Again, a spectrum hole, when you see a vacancy, we call it what? A spectrum hole. A spectrum hole is a band of frequencies assigned to a primary user, but at a particular time and specific geographical location, the band is what? It's not being used at all. Okay, a cognitive radio, again, intelligent radio, aware of the surrounding environment and so on and so forth. It can adapt. By the way, it can adapt to corresponding changes in what? In the operating frequencies, in the power, transmit power, in the carrier frequencies, the modulation techniques, and so on and so forth. It can what? Adapt from one to the other. Clear? Okay. Requirements and the properties of the CR. Again, as I told you, it needs to be able to coexist with what? With the legacy wireless systems. What is legacy wireless systems? Legacy wireless systems are those which are in operation right now, not cognitive. Yes? Operate, coexist with the legacy wireless systems, use their spectrum resources. It uses their spectrum resources, but does not what? Interfere with them. They are paying big bucks. Clear? You are getting it for what? You are getting it for free, jumping from one to the other. Clear? Okay. Properties are a technology that listens to the spectrum. It's like sensing the media. It's similar to the Ethernet. Listen to the spectrum. Knowledge of the primary user spectrum usage as a function of location and time. Rules of sharing the available resources in time and frequency and space. And then what? Embedded intelligence to determine what is the optimal transmission parameters, such as the bandwidth, the latency. Latency means delay. QoS stands for what? The quality of services, and so on and so forth. Clear? So you start with what? You start by what? Sensing, characterize it, react, adopt, and then what? Go back, and so on, so forth, so on and so forth. This one you can see how it is what? How it's crowded, but this one tells you what? Even though it looks crowded, but most of the time it is what? It is empty. Did you get this or not yet? Some of you did, some of you didn't. Did you get this or not yet? Who did get this? Did you look at it? Is it crowded? It's crowded. By the way, even the one that you got might not be the latest one. Unfortunately, they are not updating it. They are changing. By the way, this one here, they took the analog TV channel. The FCC took analog TV channels, and they are going to assign it to the what? Assign it to the new fourth generation, and so on and so forth. This is, again, the diagram of this. Clear? Clear? Okay, good. Now, let's start with the what? Let's start with the modeling. And I'm going to start with the nonlinearity first, before the what? Before? The other one. Huh? Even though it says part 1, I will start with the nonlinearity before the what? Noise model. Reason is that because after we finish this, I need to show you the effect of both on the link budget. On the link budget. Link budget depends on what? It's noise is more than what? More than the nonlinearity. Clear? So I will start with this, and then I will come back to this, if you don't mind. Actually, whether you mind or not, I don't care. So I take that back. You don't mind, I don't care about that. Okay, so let's look at what? Let's look at the nonlinearity and the distortion. Clear? Always remember, the nonlinearity will what? Will determine what is the what? The highest received power possible, not the lowest. Are you following me or not? In other words, we are not talking about what? Sensitivity here. Let me show it to you so that you understand what I'm talking about. I want you to see this diagram here. Okay, this is premature, but I want you just to get a look at it. This is what? This is the nonlinear characteristics of our amplifier at the receivers. Is this at the receiver or at the transmitter? At the receiver. At the transmitter, I don't worry too much about this. Did you understand that or not? Okay, this is at the receiver. What is this? This is the fourth fundamental. What is this? By the way, what do you notice the slope? This is the third order intermodulation. Are you following me or not? Okay, and we will see why is this one, is the slope is 3 times as this one. We'll see that. But I need you, first of all, to understand that this is in what? In decibels. Everything is in decibels. So this one is what? In dBm, which is power, output power. This is what? Input power. Did you get this or not? Okay. At this point, by the way, what is this, the slope line? Do you see this slope? Sorry, do you see this line? This line is if the characteristic was what? Were linear. Are you following me or not? The point where it deviates by 1 dB. Do you see this 1 dB from here to here? This is what we refer to as a what? The 1 dB compression point. Remember the 1 dB compression point is the point where this one deviates from the actual characteristic by 1 dB. Clear? The 1 dB compression point, you can measure it from the input point of view side or from what? The output side. Yes, they will be related together by what? By the gain of the amplifier, the power gain. Yes or no? Okay, good. Now, what does this point mean? The point when the output fundamental power and the output third order intermodulation, if it was what? Linear. Are you following me or not? They intercept. This is what is known as what? Did you get my point or not? Yes or no? In other words, you sketch the what? The linear approximation of what? The fundamental curve. And you sketch the linear approximation for the what? A third order intermod. Where they intercept is the what? IIP3. Clear? IIP3 stands for what? The third order intercept point from which side? From the input side. This is called what? OIP3. OIP3 stands for what? On the output side. Again, is the third order intercept point. But as related or as measured where? At the output. What is the relationship between this one and this one? Where is it? Here. I'm sorry. Here. What is the relationship between this one and this one? just with the gain. In other words, if you add the gain to this one, you will get what? You will get this one. Clear? I will show you that in just a second. Now, I want you to see this. What is this? DR. What is this DR? DR stands for what? Dynamic range. This is the what? Difference between this one and the what? The low noise level. The low noise is what we refer to as what? The sensitivity, or the what? MDS. MDS stands for what? Minimum detectable signal. It's the minimum detectable signal, the weakest one. Yes? What determines the minimum detectable signal? Is the noise. What determines the maximum one? Is the nonlinearity. Did you get this or not? This minus this is what is referred to as what? The dynamic range, linear dynamic range. Then we will study another dynamic range, which is called what? The spurious free dynamic range. We don't know what that means. Yes? We don't know what that means yet. But it is the difference between what? It is the difference between the, you see the third order intermodulation? When he intersect with the what? With the noise level, and then you extend what? You extend all the way to the fundamental stuff. Clear? That is called what? The dynamic range, the spurious free, which means what? No spurs. The dynamic range of the receiver. Clear? But we'll talk about that shortly. I just wanted to show it to you. Did you understand it? Okay, good. Now let's get back to the analysis. So we have the nonlinearity distortion. We have what? Remember, by the way, one more time. A linear system is a system that does not create new frequency components. It can attenuate, it can amplify. Are you following me? Not existing frequency component, but it cannot what? Create. Clear? All the devices that we are going to be looking at the receiver are what? Are nonlinear. By the way, even if they are linear, they are time varying, which makes them what? Which makes them their behavior as a what? Nonlinear behavior. Clear? We'll talk about that shortly. We are going to be dealing with those circuits. Harmonic distortion. Harmonic means what? Second harmonic, third harmonic. How many inputs? One input or multiple? One. From the harmonics, you only get when the input is a what? It's a single component. Yes or no? Whereas the intermodulation, you need at least what? At least two components. At least two components at the what? At the input. Clear? Clear? Okay. Okay. And then amplifier gain, the 1 dB compression point, the blockers, the receiver dynamic range, all of these issues. Now, this is, again, as I told you, the linear and the nonlinear module. Notice, by the way, in here, is it linear? This region, is it linear? It is linear, but the problem is what? I am not getting the full efficiency of my what? My amplifier. I'm not operating the amplifier in a what? In a most efficient way. Clear? Clear? So even though but there's no other way around it if you are going to use modulation schemes that are what? Non-constant envelope. If you use non-constant envelope, which I'll show you later in detail, non-constant envelope with non-linearity, all of these what? The side lobes that you got rid of when you did the channel select, at the transmitter will what? Will reappear. Are you following or not? Will reappear again. Clear? So you need to operate in the what? In the linear region. And that is why we call the non-constant envelope modulation scheme, we call them what? Power inefficient. Are you following or not? They are what? Bandwidth efficient, but they are power what? Inefficient, because you are operating the amplifier in a what? You are operating the power, the amplifier in below the what? Below the, or backed off. You backed off from the maximum to the what? To that region. Clear? Let's see how we model it. We have a what? We have a system. This is the system. Nonlinear system. And you are applying the input. Let's call it Vi of t. And this is the output. V naught of t. Are you following me on that? What does V naught of t look like? It looks like a DC. By the way, is there a possibility that there is no DC component? There is a possibility that there is no DC component. I just write it in general. C0 plus what? C1 Vi of t. Is this the one that I'm interested in? That's the one that I'm interested in because that is the fundamental component. Are you following or not? Yes? This one, all of these are what? are the nonlinearities. Are you following me on that? Or no, don't call those harmonics. Call them what? The nonlinear terms. Their effect is to generate the what? The harmonics and the third order intermodulations and so on. So clear? Clear? Oh. Now, in our course, we are only going to stop at what? At the third order. We have better things to do than to write what? All of these cosine terms and stuff like that. Clear? And I will give you next time, or I will be posting a table that shows you what? That shows you all the components at the output up to what? Up to this, so that in the midterm you just can what? Plug in, as long as you know what you are doing. Are you following me or not? Clear? Okay, good. Now,
Professor, we have 5 minutes left.
oh, thank you. Okay, let's look at what? We spent time on this early thing. I thought you already know it. Okay, let's look at the harmonic distortion. How many inputs? Only one input. Now, I need you to understand one thing. In here, I'm assuming that the input is a pure sinusoid. Agree? In reality, is it a pure sinusoid? It's a pure sinusoid. Sorry, it's a sinusoid along with what? It's modulation. Yes or no? But this is just to show you the problems with the what? With the nonlinearity. So I am applying VI of t equal to what? VI cosine omega naught t. Yes? What is VI? What is VI? VI is the what? Is the amplitude. It's the peak amplitude. Clear? And omega naught, of course, is the what? Is the 2 pi f naught. Clear? Okay. So it goes through the nonlinear amplifier, which is this. What am I getting at the output? C naught. This is the constant term. Plus what? C1 VI cosine omega naught t. What happened to the omega naught t? Everything is omega naught t. Are you following me or not? Okay, omega naught t. This term came from who? From this guy. Yes? Okay. Notice, by the way, this term came from who? Came from this guy. Yes? And so on and so forth. I will stop it here. Then what? V naught equal to what? C naught plus what? C1 VI cosine omega t. Yes? Where did this come from? This cosine square is what? 1/2 plus cosine this. Yes? And what is this? This is C3 VI cube. And the cosine is what? It's cosine. Cosine cube is what? Cosine times what? Cosine square. Yes or no? So I get this one. Did you get this or not? Now, I want you to see the following. I want you to see what did the what? The input is at what frequency? By the way, you notice, am I sketching the spectrum as a pure delta function? Ideal or not ideal? It's ideal. But just imagine, what did it generate? Tell me, what did it generate? DC, the fundamental, yes or no? How come the fundamental is larger than this? How come the fundamental is larger than this? There is amplification. That's why we call it an amplifier. Are you following? Why do we call it an amplifier? Okay. The second harmonic, where did the second harmonic came? Show me the term. This one. Yes? Third harmonic came from where? Here. Notice, by the way, the first harmonic, I have a term here, and I have a what? A term here. Did you get it or not? Okay. This, when I say term here, means what? This one. Yes or no? Cannot hear you. Now, notice, by the way, if this is the received signal, this VI is very small. You agree? When you take the cube of it, it becomes even what? Smaller. Are you following me or not? So the effect of this, not this, sorry, the effect of this is what? Is not relatively what? It's negligible. Are you following me or not? Now, let's see if you can help me the definition. I want you to remember all of these definitions. Not for the midterm, but for what? For the field, for the wireless. They expect you to know all of these things. When they talk about harmonic distortion, ratios of what? Voltages, not powers. Did you understand that or not? So, yes or no? Let's see. HD2. What is HD2? HD2 is the second harmonic distortion. HD2. Looks like Star Wars. HD2. Yes? Second harmonic distortion. What is it? It's the amplitude of the second harmonic divided by what? The amplitude of the what? Fundamental. Give it to me. Where did this one came from? It's 1/2 C2 BI square. Did you get this or not? Yeah. What is the denominator? C1 VI. Question, how come this term was not included? Because we are assuming that VI is what? Is small. If you want to be really precise, the denominator should be what? C1 plus, help me, 3, C1 VI plus, help me, 3 C3 over 4 VI cube. Did you get this or not? But I ignore this. It's very small to begin with. Are you following me or not? Yes or no? Okay. Now you might say, Professor, also ignore it in the numerator. By ignore it in the numerator, you don't get any distortion. So what are we talking about? Did you understand that or not? The denominator is an additive term. Clear? What do you notice? You notice it is 1/2 C2 over C1 VI. I want you to understand, the point is not to just look at the equation. Understand the ramification of it. The second harmonic distortion is proportional to the input voltage. Yes? Whereas the third harmonic distortion, which is the definition, by the way, is what? Is the amplitude of the third harmonic. Where is it? Show it to me. Where is the third harmonic? This guy.
Professor, we're out of time.
1 minute, please.
Okay.
1/4 C cube VI cube divided by what? C1 VI. You see that it's proportional to the what? Square of the VI. Which means what? If VI happens to be what? Relatively high, the third harmonic distortion will be what? More severe. Clear? I ran out of time. I wish the time stops for a minute. But in any case, we'll continue next time.
This concludes today's session of EE 544 on Tuesday, February 4th, 2014.